So, hello everyone, and welcome to another IMechE postgraduate webinar. So, these webinars are part of a continuing series of webinars which were started last year, and they're hosted every month. And the aims of these webinars are providing opportunities for PhD students and postdocs to showcase their work. So, we're looking at the most recent work in tribology that is ongoing right now. So, my name is Ben Wainwright. I'm going to be chairing today's session. So, today we have two presentations. The general format of this webinar will be such that each presentation will last approximately 20 minutes. And then immediately after each presentation, there'll be an opportunity for some of your questions to be answered. So please feel free to write your questions in the channel while the presentation is ongoing. And we'll make sure that as many are answered as possible at the end of each presentation. So without further ado, I'd like to introduce our first presenter, David Macmillan of University of Central Lancashire. So David graduated from UCLan with a master's in mechanical engineering while working in the maintenance industry for 8 years. David is currently a third-year PhD student whose project focuses on developing a tribotronic tilting pad thrust bearings to reduce energy losses. David, over to you.
Thank you for the introduction. Can you hear me well, Ben?
I can. I'm going to go on mute now. Good luck, David.
Okay, thank you very much. Yeah, so my name is David Macmillan, and I'm currently in my final year, a PhD student at the University of Central Lancashire within the Jost Institute for Tribotechnology. And today, I'm just going to be talking to you about the development of a new test apparatus, which has been developed at the university for the evaluation of an active geometry tilting pad thrust bearing. I'm going to kind of give you an overview of tribotronics and active control. The outline of today's presentation, I just want to give you an overview of the energy losses in tilting pad thrust bearings, some of the optimization goals in tilting pad thrust bearings, the tribotronic design concept, slightly go over a COMSOL thermohydrodynamic model I developed to look at controlling different aspects of the bearing to reduce power loss, and then finish with the experimental test apparatus. So I'd like to draw your attention to these two pictures here on the right-hand side. It's a picture of a hydroelectric turbine at the UK's biggest battery in Wales. And this large turbine shaft is supported by a tilting pad thrust bearing. And generally, the losses due to these tilting pad thrust bearings in these particular applications can extend up to megawatts. So a large amount of energy is consumed to overcome friction within these contacts. So there's a large driving force to try and reduce the energy losses in these contacts. For those who aren't familiar with the tilting pad thrust bearing design, it's a hydrodynamic bearing or a fluid film bearing. It utilizes a number of independent sector-shaped pads, which each tilt upon a fixed pivot to form a convergent wedge geometry. These pivots are either line pivot or point pivot to allow it to tilt circumferentially and radially in terms of a point pivot. Now, since the initial design was patented over 100 years ago by Michel and by Kingsbury, it is conventionally remained a passive device in that it requires no external control to function. These pads tilt to form an equilibrium condition based on the operating conditions. But now the limitations of the passive operation are being challenged to push beyond the passive design limits. And one of the main limitations of the passive operation is the inability to effectively adapt and change its optimization goal during operation, and also respond to system disturbances such as differences in lubrication supply and differences in operating conditions. So tribotronics or active tribology, active hydrodynamic bearings, are a relatively novel and recent design initiative looking at reducing losses in the contact due to friction, wear, and vibration. by integrating sensors within the contact, controllers combined with a control law and control scheme, and then actuators which actuate a proportion of the bearing, some particular variable within the bearing. My work at the University of Central Lancashire in my PhD project is specifically focusing on implementing a controllable pad arrangement for the reduction of shearing losses in the contact. And I've also developed a test apparatus for performance comparison, benchmark predictions due to the passive design and comparing that with the novel tribotronic design. There are two sources of energy losses in tilting pad thrust bearing. This is the turbulent churning and mixing of the oil in the unloaded oil reserves throughout the housing. And then there is the power converted to heat due to shearing. So as we can see in figure 2, this is the lubricant flow path. There is a cool supply of oil typically supplied in between the pads in some cases. Other cases it's just fully flooded. This oil is then turbulently churned and mixed with hot oil carried over from the previous pad. It is then dragged by the thrust collar into the wedge, where it is then sheared. This power is then converted to heat. This heat is then largely advected and taken out by the lubricant, out of the bearing, recycled and replenished. But some of the heat is also conducted into the thrust collar and the pad, which can also cause thermal deformation of the pads and collar. On the figure 3 is the proportion of power losses in the tilting pad thrust bearing. So a large proportion of power loss is consumed due to the shearing, and this is a necessary component of hydrodynamic operation. There's also a significant proportion consumed by churning of the oil. And this is typically churning at the collar periphery, so in the groove above the collar in the housing, and also in the space between pads and the collar internal. Now, the proportion of churning losses tends to increase at higher thrust collar speeds. But there has been incentives, especially in the 1970s, to design directed lubrication supply systems so that the lubricant is directed straight to the wedge instead of all these parasitic losses due to churning. And these directed lubrication supplies were things such as leading edge groove supply and spray feed. There are multiple objectives for optimizing tilting pad thrust bearings, such as maximizing the film thickness during transient conditions, startup, shutdown, and low speed operation, and trying to push from at lower speed, trying to push from this boundary contact to the hydrodynamic operation. Then there is minimizing the maximum pressure at high load operation, or designing bearings which can support substantial loads with different materials such as PEEK or PTFE, which can have a higher power density and they can support much greater loads. There's also minimizing the maximum temperature in the contact, minimizing the maximum temperature in the bearing at the higher speed operation. So in applications such as centrifugal compressors, gas and steam turbines. And there are also designs with cooling coils and so forth to try and excavate a lot of that heat and keep it within its safe operating region. And then there is designs to optimize the stiffness and damping due to dynamics of system, so system vibrations, designs for squeeze film dampers and such to optimize these dynamic characteristics. There's also minimizing wear in the mix and the boundary at low speed where you have surface contact. And what I'm looking at is minimizing power loss in the stable hydrodynamic operating regime where you would tend to want the bearing to operate for most of its lifespan. So these are the passive design limits, and they haven't completely been achieved. So there are still a lot of design and research going into trying to improve the passive design limits. Things like surface texturing and different materials and coatings. But slightly ahead of the curve is active control and the next evolution of tilting pad thrust bearing design to be able to characterize these performance characteristics and optimize a proportion of the bearing. For those who are unsure what tribotronics is, it's an amalgamation of tribological component, tribological interface with electronics. So this is just the passive design. As you can see, there's inputs which are the operating conditions, such as the load, the speed, and the lubrication supply, and then the outputs of losses and friction. Now, the bearing can't react to these losses and provide feedback to optimize different characteristics. With tribotronics, it's utilizing sensors to measure power loss, film thickness, utilizing these sensors to measure these characteristics, and then making an informed decision combined with a control unit and an optimization goal or an objective function, in this case to minimize power loss, and then an actuator to control either, there are two typical categories, would be to control the film geometry or to control the lubrication in the contact. And modeling, I developed a model earlier on in the project to look at controlling the oil film geometry specifically. So this model is a thermohydrodynamic model developed in COMSOL multiphysics, and it's just a steady state film, steady state condition. So there's no time dependencies of the oil film geometry. And with a pivot, with a pivoted pads, you have the film function is defined by the height above the pivot, the film height above the pivot, the tilt angle and the roll angle, and then the position of the pivot. It also combines the pressure generation due to the 2D Reynolds equation, which is commonly used, oil film heat transfer, the energy equation, leading edge temperature due to this hot oil carryover and what the leading edge temperature is, and the temperature dependence of viscosity, the viscosity in the oil film determined by the Vogel equation, and then finally the load and moment equilibrium. Now, the load and moment equilibrium is to determine what the film function is dependent on the operating conditions, as you don't actually typically know what the film function is. So on the top right hand side, you can see the temperature variation in the film. So we have a slightly higher inlet temperature, slightly higher than the feed temperature to the bearing due to this hot oil carryover, and then we have this thermal distribution. And then on the bottom left is the Vogel equation and the viscosity variation in the oil film, and then the pressure distribution and the film geometry obtained. This model was validated with published experiment. And on the left-hand side, you can see a 1D pressure plot comparison with experiment, which shows good agreement. I won't go too much into it, and there's also comparisons with power loss at different rotational speeds. You tend to see, because I'm only taking into account the shearing losses, you tend to see a larger deviation at higher rotational speeds, because it's difficult to effectively determine the losses due to churning as well. The tribotronic elements for the conceptual design, it utilizes capacitance-based oil film thickness sensors for feedback to determine the pitch angle of the pad. These actuators either apply a displacement to the pad or a force to the pad, which then tilt the pad to obtain a given pitch angle, which is optimized for power loss or for maximum load carrying capacity or changing the film forces in the contact. And I'm just looking at a low-cost mechanical actuator, but for time responses, it may look at including actuators such as piezoelectric actuators, electromagnetic and hydraulic actuators. And so to solve this, it has not just the hydrodynamic moment, but also the moment generated due to the actuator force in the model. So the effect of this actuator force in the COMSOL model, I had a look plotting the power loss on the left-hand side with the actuator force. As the force increases, it increases the pitch angle of the pad and tends to decrease power loss, but you also have the consideration of you're actually decreasing the minimum film thickness. So within a control system, monitoring the minimum film thickness, monitoring the film thickness in the contact, monitoring the power loss, you can change the optimization goal during operation and actuate and effectively tilt the pad using control. For dynamic response, it would be looking at the actuator force in time and changing the angular acceleration of the pad to control film forces and maybe negate some vibrations in the system. Finally, onto the experimental test apparatus, which has just been commissioned and was developed over a year. There is a 4 kilowatt motor with speed control from 0 to 3000 RPM. This motor is connected to a jaw coupling behind here, and then this jaw coupling is connected to a drive shaft with a collar at the end of the drive shaft inside the housing. This is a fully flooded housing which contains the thrust collar and the tilting pad thrust bearing. There is two load cells. There's an axial arm, a torque arm load cell and an axial load cell. So you can measure the axial thrust load, and it can also measure the torque applied to the tilting pad thrust bearing. There is space for pad actuators when the design has been finalized to implement the particular actuators for control. There's a tribo sensor gland which has the output thermocouples which are introduced onto the pad, and capacitance-based oil film thickness transducers. This it's a dual shafting configuration, so this side of the shaft is able to rotate, and it's able to rotate so that you can measure the torque on the on the torque arm load cell. There are alignment wheels to align the tilting pad thrust bearing face with the collar. And there is a combined linear and rotary bearing, which allows the bearing to be retracted from the tilting pad thrust collar face. And there is a loaded angular contact ball bearing. So a thrust load is applied by a hydraulic press here through an angular contact ball bearing, and then forces the tilting pad thrust bearing against the collar. There is DAC and controller, which has all the temperature thermocouples, has the capacitance film thickness transducers, and then there is the circulating oil supply, which can control flow rate into the bearing, can control temperature, and pressure control as well, just for the circulating oil supply system. So these are just an overview of the test measurement capabilities. It has power loss measurements, which is the lubricant flow energy balance. That's a typical industrial method. It measures the difference between the feed temperature and the drain temperature and the flow rate, and determining the density of the lubricant and specific heat capacity. Also have the direct torque arm, which is typically a laboratory setting measurement, for improved and more precise measurements of torque, because the problem with the industrial method is that it only determines the temperature variation in the fluid. A lot of the heat is conducted into the pads and collar and radiated. So this heat is lost, so it doesn't give a full picture of the amount of energy losses in the bearing housing. There's also the tribo sensors, which is film temperature and film thickness. It has a maximum bearing outer diameter of 130 millimeters. There is a maximum load of 25 kilonewtons. This is restricted to 25 kilonewtons due to the load applied to the rolling element bearing. And there is a maximum speed of 3,000 RPM. There are test capabilities of various viscosity grades, from medium to heavy turbine oils, typically used in gas and steam turbines, so a thinner lubricant. Lubricant supply control, flow rate control through a needle valve from 0 to 3.5 liters per min, maximum oil tank temperature of 70 degrees, and a supply pressure control between 0 and 2 bar. It has the retractable shaft, which enables bearing access without these realignment issues. So you don't have to disassemble all the system. You can just retract the bearing from the collar, take the bearing out and analyze the bearing. And then there is rear bearing space for actuation and modifications. And there's just a video of it operating. So that was operating at 3,000 RPM and a load of 16.8 kilonewtons. Finally, to conclude, the proposed design is to actively control the oil film geometry, just looking in the steady state at the minute, just to looking at reducing power losses using geometric actuators. The test apparatus has been developed to compare this novel tribotronic bearing with a conventional passive bearing. The test apparatus includes data acquisition from various sensors for steady state performance evaluation and feedback for control. Future work is to validate the control strategy for power loss reduction. Comparing the performance with the conventional bearing, that's the next stage, is getting some results for the conventional bearing. And then finally looking at developing a closed loop control law using autonomous actuation. And there are further possibilities, a lot of possibilities with this test rig, investigating control during startup and shutdown periods and how that influences maybe the lift off or the friction during these conditions. Investigating load and thermal distribution improvements by independent pad control, and also maybe in the future modifying to be able to investigate dynamic characteristics and time dependent control, and also investigate different actuators in the future. So thank you all for listening, and any questions?
Well, thank you very much, David. That was a very interesting presentation. We do have a couple of questions from our listeners. So Philip Healy has asked, related to the relative power losses and force limitations for alternative maglev solutions, and whether from high coercivity of permanent magnets or electromagnets.
Well, I think the active hydrodynamic bearings have evolved from the control in magnetic bearings, the control that you can apply forces to the rotor. But the problem with the magnetic bearings is the lower load carrying capacity, and the bulkiness and the cost. So this has kind of driven moving the active control into the hydrodynamic bearing design, I think. So I think that slightly covers it.
Yeah. Thank you. Another question from Katano Peng. Are there any differences in the tribological behaviors between vertical and horizontal shafts? And what are the locations of wear on the pads? So 2 questions there.
Yeah, so are there differences? Yeah, so there are definitely differences based on, especially in the control side of it. So a lot of control has gone into particularly tilting pad journal bearings, and the controllers focused on changing the rotor position and optimizing the stiffness and damping. And that's because journal bearings also provide rotor position control, as opposed to thrust bearing, which is just supporting large axial loads. So it's not really used for positioning the rotor and the rotor dynamics. And the locations of wear on the pads, it depends on the type of wear. Basically, it depends on what sort of wear and what sort of conditions it's under, but typically you might see a lot of wear that occurs due to towards the trailing edge. You'll definitely see a lot more wear towards the trailing edge, especially when it's highly loaded. The film might disrupt, and you might have a large, significant amount of wear towards the trailing edge. You also have wear on the pivots as well, due to high loads and things like that.
Thank you. If I could add to that question, what are the main failure modes of these bearings?
What are the main what? Sorry.
Failure modes of these bearings.
The main failure mode: disruption of the oil, high temperatures, bearing wipes. So the lubricant film gets decreased so much that you have surface contact. There are also abrasive wear as well onto the pads, changing the system. You also have, especially in the larger pads, you can have thermoelastic distortion and things like that.
Thank you. And one last question before we move on to our next presentation. Muna Hamdith asks, how are film thickness and lubricant temperatures measured in your testing?
In the test rig, the film thickness is measured by capacitance-based transducers. So I built these myself. It's just a coaxial cable. The coaxial cable has on the end, on the sensor probe, it has an iron hypodermic, and there's an electrode. And this measures the capacitance between the pad surface and the thrust collar. Based on that, combined with the amplifier, it measures the voltage, and then the voltage is fed back into the DAC device. But I have to calibrate these sensors with either with a micrometer to determine what voltage drops you get for different displacements. So the capacitance based, and the lubricant film temperature is measured by thermocouples imposed on the pad. Typically, in industry, they use subsurface pad temperatures and not specifically thermocouples, which are introduced at the film.
Thank you. I think we'll have to move on there. There was one more question left, but if David, you're happy to share your email after this, perhaps that person could contact you directly for that question.
Yes. Yep.
Okay. So at the end, we'll share emails of the presenters for anyone who has any further questions to ask them. But for now, we'll move on to the next presentation. So the next presentation is by Joseph Jaffé of the University of Sheffield. He is a PhD candidate researching how changing conditions impact the friction of leaf contamination across railways. Before starting his PhD, he graduated from Sheffield with a master's in mechanical engineering and has been working for a medical device company in industrialization as well. Thank you, Joseph.
Can you all see my screen?
Yes, we can see your screen.
Fab. Right. Yeah. Good afternoon, everyone. I'm Joseph Jaffé, like Ben said, and yeah, I'm a final year PhD student at the University of Sheffield. I'm working on rail tribology and specifically leaf layers. And today I want to give you a bit of a talk about how the new methodology that we've been coming up with to create leaf layers for that tribo testing. On the 31st of October 2021, two trains collided at Salisbury Tunnel Junction. 14 people were hurt and the driver suffered life-changing injuries. The investigation points to low adhesion on the rail, impairing the ability of the second train to brake. And you can see from this image that the rails were severely contaminated, especially when you compare it to what a mainline rail should look like. Here you can see the extent of the contamination as well as how much leaf fall there was around the track. This is an extreme example, but it's just one of hundreds of signals past at danger, station overruns, and slides that happen every year on the UK rail network due to low adhesion. Leaves cause low adhesion when they fall onto a rail, mainly during autumn. The leaves are then crushed by repeated train passes, and that creates the characteristic black leaf layer that's shown here. The leaf layer is extremely slippery, especially when combined with water, and it reduces traction levels well below what's required for safe braking demand. So for train operation, for traction, for braking, you need at least 0.1 coefficient of friction, and leaves take you well below that. They've been measured down to 0.01, but they're normally kind of take you to that ultra low regime where you're down to 0.0, half of what you need for safe braking or traction. The specific mechanism of low adhesion is not fully understood, but there are some competing different mechanisms based around shearing or hydrogels, etc. Got a video here of an example of the issue. This narrow gauge rail is trying to apply traction, and it's basically just coming to a dead stop because it can't get any grip on the rail, and the leaf layer between the wheel and the rail is just meaning that it can't apply any traction. The main safety issues with trains, though, is them being unable to brake safely and efficiently. And every autumn, this means that the network has to run reduced timetables, which allow for longer braking distances and slower running speeds. And this costs approximately £355 million every autumn in performance, safety impact, and prevention costs. So, looking at studying leaf layers, this is the problem. So, when you want to study naturally occurring leaf layers, it's pretty challenging. They're usually inaccessible for researchers, so accessing mainline rail is really challenging. It requires a really long lead time. There's quite a lot of safety provision because you basically have to have support from Network Rail. You have to have protection so that you're not going to be hit by a train. And this requires a lot of preparation in the start. It leads to research being done on alternative railways like the Vale of Rheol narrow gauge, which is shown in this picture. The problem with them being inaccessible and needing a long lead time is that they're also transient, and so you might not know when they're going to be there. They are very dependent on weather conditions and train movements, especially early in their formation. We know the peak time of year, so that's about the start of November, but not when they will form exactly. And they can be brought forward very quickly by a storm, which brings down all the leaves, or they can be delayed by warm weather. Finally, they're season limited. As you'd expect, the leaves fall in the autumn, and in some locations, the leaves will stick around and the leaf layers will stick around until about February, but it's still quite a short window. And even with climate change, which is pushing autumn back and actually extending autumn quite a lot, autumn in quotes for us, basically where the leaf layers fall, railways are still under pressure to maintain their services and get rid of it, clean the rails quickly. So access is extremely limited. This means that we need to generate leaf layers for our research. And these generated leaf layers have to have quite a few different attributes. They've got to create that ultra low or low adhesion, otherwise there's no point in us doing it. You have to be able to create them all year around. It's no good having something that is limited like the real leaves are. And they've got to have similar physical characteristics, similar thicknesses, and similar reaction to moisture. Some nice to haves would be that it's well bonded, so that it creates a really strong bond between the layer itself and the rail. And we also want to potentially see the color change, the chemical changes that we see in real leaf layers, but those are nice to haves. Some of the current solutions, paper tape has long been used as an industry standard to replicate leaves. It's easy to lay and creates the ultra low adhesion required when it's been wetted and run over. The way that you lay it is you run the track trolley that you can see in the picture along the rail. The tape is laid, and then you wet either with a spray bottle or a train that's got water sprayers on it, and that can create the ultra low adhesion that you're looking for. It's well bonded, thickness is approximately similar to leaf layers, and it is made of some of similar materials like cellulose, but it doesn't really have any of the chemical characteristics of leaf layers. The other method that's used is whole leaves, and this is where you tape whole leaves to the rail. It's effective because it's exactly the same as the process that happens in nature, but you're just forcing it to happen by using the tape to hold the leaves in place so that they're not blown away and that they stay for repeated train passes. Low adhesion has been achieved using this, but there are a lot of drawbacks. It requires fresh leaves, so you have to collect the leaves in the autumn, and they don't really keep, they get quite moldy. And it's very time consuming to complete, especially if it's windy or raining. And you often need 3 pairs of hands to do it, holding down the leaves, taping, all that kind of thing is quite challenging. So the new method that we've created, this method was first tested in the lab on a linear full-scale rig, University of Sheffield, pictured here. The material used was dried leaf layers, so sycamore collected from our local park, dried, and then blended and sieved into this powder. And we use the powder to make a paste with water in a 1:4 powder to water ratio, and then it's applied to the rig. The rig works by hydraulically exerting a normal force through the wheel into the rail, and while the rail and wheel are pulled separately, you can create slip between the two of them. So for this work, the rig was run at 100 millimeters a second with a normal load of 70 kilonewtons and a slip of 3% between the rail and wheel. This gave us a contact pressure of about 1.1 gigapascals, which is kind of average or standard for a kind of passenger train. The paste was applied to the rail, and here it is before any passes. Here we have it after 10 wheel passes, and here it is after 20 wheel passes. Lots of materials being pushed from the contact, and the characteristic black coloration, which we see in the field, has appeared very quickly. Here are the results from the lab. So at the top, the blue line, you've got a control. That was just a dry rail tested for the same number of cycles. And then the orange, purple, and yellow are the leaf layers we created, well below that level required for effective braking and acceleration, and quite consistently staying at that ultra low adhesion regime, which is really positive. It's the first time that ultra low adhesion has been achieved in a full-scale linear rig using leaf materials, so that's really positive. Here's a picture of what they look like. You can see that characteristic black coloration on the right-hand side where the contact band is, and we chemically assessed them using a handheld FTIR, and saw some significant chemical changes. At the top, you've got the powder before it was applied to the rail, and then these 3 lines are the 3 leaf layers we made. Purple is the is just the dry rail, the control rail. It was also compared to some layers that we found in the field and looked very similar, so that's really positive. The next step was to take this testing into the field, and it's the same, completely the same method, but it's a much larger scale. You can see some of my colleagues here using a bucket. We're using buckets and kind of home scales rather than lab equipment because we're covering a large area, but it's the same process. You make the paste, you prepare the rail by sanding it slightly with a wire brush or something to expose the raw steel, and then you put the paste down like we were doing in the lab. Because it's wet, it can't blow away, and we don't have to use tape, so it's fantastic. Here's some prepared sections for some electrical testing that was going on earlier this year. So here's some observations from the field. This is a train going past at 10 miles an hour, but slowed down. And you might be able to see that quite a lot of material is thrown out by the first layer pass. This is obviously, we realized after a few tests that because we're going at 10 miles an hour rather than 100 millimeters a second, we needed to add a lot more material because that first axle was throwing out a lot of material. And so that's something that we adapted for the field. But here's a picture of the final product. It might be quite hard to see on the screen, but that's great from my point of view. You've got this black, thin black leaf hair that's really well bonded. You can't scratch it off with your nail, anything like that. The most important characteristic, though, is the friction levels. Are we achieving the ultra low friction that we want to see? We tested this with a couple of field tribometers that the university has access to, and here are the results. So when the layers are wet, we've got that friction down into the ultra low regime, well below safe braking levels, or below safe braking levels, but also significantly below the kind of rail baseline that we took before we did any of the testing. So just testing the rail before we apply any material to it. The layer also exhibited this kind of two-speed nature that we find in the field. So when it's dry, you might have a wide range of values, most of them actually in the safe area, which is which we find in the field. But then when you apply water, it seems to be activated, or that puts it into the ultra low or low adhesion regime. So the dry is how it was found after the train had gone after it, and then wet is when we apply water with a spray bottle. And this was to create more autumn-like conditions because most of the testing we were doing was occurring in May and June, and it was really hot. We had about 20 degrees some of the days we were testing. So we were adding that water to kind of simulate high humidity or the dew that you might see on an autumn morning. Other characteristics were tracked, such as layer thickness. The layers created were really thin, and they matched this survey data. So in 2007, there was a survey of layers that were found in the field, and most of them were sub 100 micron thickness, and we're seeing that in our layers, which is fantastic. We also saw this relationship where after the first axle passes, or the first train pass, you've got a significant reduction in thickness as you'd expect, and then the change between each train going past tapers off. And you can see this is a study from Japan on a scaled rig using a different type of lead and a slightly different method, but we're seeing this same relationship that when the first, you start with a quite thick layer, and then it very quickly becomes very thin, and the change is reduced. We were also tracking the moisture content of the layers, and here you can see the results. This is what you'd expect on in dry weather where there's no rain, no extra moisture being added from the environment. The layers start off quite quite wet, and then there's a significant drop, and then they seem to stay at quite a dried out level, but then they maintain that level through repeated cycles. And here's some of that survey data from 2007 looking at moisture. It's being measured in a slightly different, it's being represented in a slightly different scale, but it's the same method of wood moisture equivalent, and our layers were matching up to a lot of what was found in the field. So that's really heartening. So what's next? Well, the fact that we can easily recreate leaf layers in the lab, that really opens up the possibility of what we can do. Here's a graph that we made at the time, kind of a pilot study looking at adhesion recovery. The dry rail had some oxides on it, and it recovers quite quickly to dry standard levels of adhesion. The wet rail, the blue line, does eventually recover, but it takes a while. And the green line, which is had a leaf layer on it, as I described earlier on, prepared in the same way, is persistently staying at that low or ultra low traction regime, the dangerous area. That's 50 wheel passes. That's about 5 trains, depending on their length. So it's really interesting and something that I want to explore further. The fact that we can create leaf layers on full-scale rail also means that we can create a layer in the lab and then take it somewhere else and do other testing on it. So I've created layers using the full-scale rig and taken them to a climate chamber, but we're also looking at taking them and leaving them outside and tracking moisture and things like that as the weather changes. In the field, we now have an effective method for making leaf layers, and this can be applied for remediation testing. There's been a lot of that happening this autumn, testing different methods of cleaning the rail. Some of it based at the University of Sheffield, looking at how dry ice could be used to clean rails with leaf layers on them. And but this brought up some new challenges that when we were actually testing in autumn, or as you see in the pictures, more like winter conditions, the method does need to be slightly adapted because it was created in a kind of spring, summer, and the amount of water we're using is quite high. But we're looking at a way of writing some standards so that it's tailored for different weather conditions. And obviously in the autumn or the winter, you can use a lot less water and things like that. But it's a great method and it works pretty much everywhere. And now we can use it to look at some different testing. I'll probably focus on how quickly moisture returns with rain after axle passes. Thanks for listening to the talk. A couple of my, or all of my collaborators are up on the screen, people who this work wouldn't have been possible with. It's been a pleasure sharing with you the new leaf method that we've been creating and how we might use it in the future to look at how rail friction changes with the leaves on it in different weather conditions. Thank you very much.
Thank you very much, Joseph. That was a very interesting talk. Yeah, lots of stuff on rail there. We have one question from our audience. Qatar has asked, what are the effects of normal loads on the adhesion of the layer, and would an increase in these loads improve said adhesion?
Yeah, I think that's a good question. So there has been, higher loads do increase your adhesion, because obviously if you had, say, a contaminant layer like the leaves, you'd break through that potentially, and you'd have more metal on metal contact and improve the adhesion. But the problem is that that's not really something we can change. The rail industry can't really make their trains heavier to react to the leaf layers. So it's not really, it would help, but we can't tell them to make the trains heavier so that they'll have better adhesion, if you know what I mean. But things like freight have different issues. So freight, which is a lot heavier normally, seems to have less issues with braking, but they do have more issues with traction and kind of getting going rather than stopping. So it does impact on what you're doing, but unfortunately, it's not something you can adapt on the trains for say autumn to make it better without putting a load of really heavy things on the train and costing a lot of fuel. Yeah.
Thank you. I've got a few questions. So, sure. Is leaf layer testing part of a standard?
We're working on it. So there's no actual standard, but the industry standard at the moment is that paper tape that I was talking about, because it's easy to lay and kind of lots of people use it for sanding trials and other things. But now that when people are looking at specific remediations for leaf contamination, you can't really use it. So we're working, University of Sheffield and RSSB are working on a standard for creating a standard test, which hopefully this will feed into.
That's great. And so when the layers are like bonded and they're bonded chemically onto the steel, how does one go about removing the layers?
So the current method for removing the layers is railhead treatment trains, which basically blast it with water. They move quite slowly and they have a lot of high volume of water jetted straight onto the rail. But the problem with those is that they basically clog up the network. They're very slow. You have to kind of reduce your passenger timetable. So the kind of new remediation methods that people are looking at, like Sheffield and different unis, are kind of things that will fit on passenger trains and clean as they go. So using dry ice or different water with abrasives in it, or that kind of thing.
So is the method nowadays to remove the layers rather than perhaps going to the source of the problem, which is the leaves, and how can we get the leaves?
Yeah, so this is quite a big topic, because obviously if you cut down all the trees, that might stop the leaves, but the problem is that in a lot of locations, Network Rail only owns a couple of meters either side of the rail, and then there are trees beyond that, and those leaves will just fall onto the rail. So yeah, in some places cutting down trees would remove the problem, but in a lot of places it wouldn't, and it's looking at cleaning and prevention in a different way rather than getting rid of the leaves, unfortunately.
Yeah, definitely in this day and age, we don't want to be cutting down any more trees.
No.
Yeah. Also, out of interest, we have another question from our audience, also from Katano Peng. What about wheel coatings, and could that affect adhesion?
Yeah, I'm sure it could. It's not something that I know that much about. The transfer of the leaves onto the wheels is like an even less well understood situation. We do know that they carry down the contamination from contaminated areas to less contaminated areas. So potentially a coating that would prevent the leaves from sticking to them would be useful. But in a way, I think that might give you other adhesion problems potentially if you're making if the wheel's less slippery. Another thing related to wheels was that this problem became a lot worse when they got rid of tread brakes, because the tread brakes would clean the wheel, and now because it's disc braking, nothing is touching the wheel surface. So yeah, something to look at potentially.
Yeah, and is there any potential to apply a coating to the rail to prevent the leaves sticking?
Yeah, but I think that the problem once again is if you're doing something that rejects the leaves, it potentially might be really slippery itself. So yeah, not that I know of, but maybe. Yeah.
Well, cool. Thank you very much for the presentation, Joseph.
Cheers.
I think we'll wrap up today's webinar there. Thank you to everyone who joined in, and if David and Joseph, if you could possibly, before everyone clocks off, if you could share your email addresses, so if anyone has any further questions about your presentations or would like to get in contact about your work. Sorry, we have one. Actually, Joseph, we have one question from Malcolm Doble. If you've got time to answer that.
Yes. Yeah. Sure.
Yes. No problems with it being late at all. So how does the leaf powder solution compare with the paper tape?
It's obviously I personally think it's better because it's more realistic. So it's actually leaves actually creating the low adhesion, but you do need leaf material in advance, whereas the paper tape is kind of a standard method. But with the leaves, you're getting the actual specific chemical bonding that's happening in the wild rather than the paper tape, which is just stuck down and run over. So I think it, especially if you're testing something remediation or how weather conditions affect it, I think that the leaf paste is a much better method. But obviously, if you're testing something like sanding or whatever, then maybe the paper tape would be a quicker and better way to do it. Especially if you've got loads of repeated tests happening. Yeah, it depends on the application. But from a chemical point of view, I'd definitely go for our method. Yeah.
Very good. Thank you. Yes, if you, Joseph and David, if you could share. Also, Ian has just said something before we wrap up. Oh, yeah. So if you could share your email addresses before we clock off. And Ian would just like to say before we wrap up to invite everyone to join the next event, which is happening next month, and to find those details for the next event on the TGC webpage. So we have a LinkedIn page now, IMechE Tribology group, but there's also the Tribology group webpage on the IMechE as well. So you can use both those locations to find more details on future webinars coming up. David, would you just share your email address for everyone,
yes,
please?
I'll just share my screen and then okay, can you see that?
Yeah, so I'll leave that up for just like 30 seconds while everyone can take a little note of that.
Mm-hmm.
And then Joseph, we'll switch to yours
Yeah.
after.
Okay, thank you.
All right, thank you. Yeah, Joseph, could you just share your email address quickly?
Coming up. Yep, just down here at the bottom.
Thank you very much.
Oh, sorry.
That's all right. So thank you to everyone who joined. And like I said, this is a continuing webinar series hosted every month. So you can check out the IMechE webpage for the Tribology group for more details. And we have also a new LinkedIn page, which will also be posting details of these webinar series in the future. And yeah, thank you all and have a great rest of the day and have a good weekend too. Take
Cheers.
care.
Thank you.
Cheers, everyone.